Chapter 7 is all about dark matter and dark energy, which are two seemingly unrelated phenomena or anomalies in modern cosmology. The first, dark matter, is an anomaly that's found in most galaxies. Most galaxies, especially spiral galaxies, are measured to possess flat rotational curves. And then what I mean by that is if you plot the velocity of each star within the galaxy at different locations, as you go from the center of the galaxy to the outer edge of the galaxy, the curve appears flat. There's always a steep rise in the beginning, and then it drops off. And if you're using the Newtonian equation, then you would expect that the drop-off to happen continuously throughout the radius of the galaxy. But what we see is that there's a flat. That is to say, the velocity of stars on the outer edge of the galaxy are in orbit throughout the galaxy at about the same speed as stars towards the interior of the galaxy. And this anomaly has prompted physicists to come up with various ideas, and the one that has stuck the most is dark matter. It's this idea that there's some substance out there. Some have suggested it's neutrinos, or there's all kinds of suggestions as to what it might be, some unknown or undiscovered particle that doesn't interact with light, but it does have gravity. And so it interacts with the other mass in the galaxy, and they're assumed that the galaxies have more mass than the velocity curves suggest. Another alternative to dark matter is this idea called MOND, or Modified Newtonian Dynamics. And MOND was introduced by Mordechai Milgram, I think is how you say his name. I think that was back in the late 80s and 90s. One of the problems with MOND, now MOND is what it does. It just fixes the equation with a acceleration constant. There's no theoretical backing or reasoning for this. There's just the addition. It's kind of like a lambda or the cosmological constant. They just kind of add it in just because it works. And it equals around 1.2 times 10 to the negative 10 meters per second squared. This would be a global acceleration. So do you know if MOND has any kind of theoretical foundations? Modified Newtonian dynamics?
Yeah, definitely. So MOND, or Modified Newtonian Dynamics, is basically this idea that tweaks Newton's laws a little bit when you're dealing with super tiny accelerations like out on the scale of galaxies. The idea is to try to explain why galaxies rotate the way they do without having to assume a bunch of invisible dark matter. So it's kind of a different theoretical framework that some people have explored as an alternative to dark matter.
So you don't know? Is that what you're saying? You don't know if there's a theoretical foundation? I'm not talking about empirical foundations. I'm talking about, is there a reason for the acceleration, the MOND constant?
I see what you're getting at. So yeah, on the theoretical side, MOND does propose a specific scale or a constant, basically this fundamental acceleration scale. And that constant is kind of put in by hand. So it's not like there's a super deep underlying theory from first principles that everyone agrees on. It's more like a phenomenological approach. I kind of let's add this constant acceleration scale into the equations and see if it explains galaxy rotation curves. So in that sense, it's more of a conceptual tweak rather than something with a fully fleshed out theoretical origin.
But haven't some people proposed that MOND is, that the MOND constant would come from the universe, kind of like a universal background, but it would come as like the acceleration from the other objects that besides the object you're talking about?
Yeah, you're totally right on that. There have definitely been some ideas tossed around that maybe that MOND acceleration scale isn't just arbitrary. Instead, it could be related to the broader cosmos, kind of like a reflection of the influence of all the mass in the universe, or some sort of cosmological background. It's a bit more speculative.
So in other words, there is no known way to calculate the Mond constant or the value of the Mond acceleration. Now, in the framework I'm proposing, we do have a way to calculate the Mond constant. It's not the Mond constant, I guess. It's pretty much the same thing, I think. There is a uniform gravitational acceleration throughout the entire cosmos. This uniform gravitational acceleration comes from the structure of the universe. This is what causes the gravitational redshift. This is what causes the horizon. This is the structure. It's the bare minimum gravitational acceleration. It's not the bare minimum. You can have I don't know. I don't think you can have a lower gravitational acceleration than this because it's omnipresent. Because no matter the further out you go, the closer you get to this 3.49 times 10 to the negative 10 meters per second squared. And so, no, it is the bare minimum. Even in the deepest, darkest voids, it's going to be this 3.49 times 10 to the negative 10 meters per second squared. Or times 10 to the negative 10. I don't know, man. That's late. It's on the screen. Just look at it on the screen. Let me show you something else. With this profile that is proposed in the previous pages, gives us this uniform acceleration, and we can use this to predict the orbital velocity of a galaxy. The only problem is that the prediction is that the galaxy curve should be rising. And so I struggled with this for a little while, but if you take a look at the image on your screen, this is a plot of a whole bunch of galaxies. There's a wide range of galaxy types on here and galaxy sizes, and it's got all of their curves fitted. And so you can see that there are quite a few curves that are rising. The smaller the galaxy, the more likely that it's going to be a rising curve. And so I think that is all we have to do is make a minor adjustment to the smallest scales, because you got to remember, this is a cosmological model that I'm proposing. It's not really meant to talk about the dynamics of a galaxy. And yet here we are. It produces a value that is 2 times the Mond value, and it causes rising curves, which a large portion of the galaxies do indeed have rising curves. And I think that this is satisfactory for me. I probably won't do much more investigating into this. This, to me, resolves the dark matter issue, especially when it's combined in with the rest of the model. When everything is taken into account as a whole, then this right here just seems very insignificant. That some galaxies have flat curves, because I mean these are the big giant galaxies. Big, giant, massive galaxies. There's going to be some that are small and some that are huge. It's not all going to create, a perfect pattern, especially when we're talking about galaxies, because this is a small scale, cosmologically speaking. And the other anomaly discussed in Chapter 7 is dark energy, which dark energy is this anomaly that's found when you map the luminosity distance relationship to the redshift data using something like a standard candle or several. You have to use several of them. You have to use at least 2, and that's not going to be very good data. You got to use, I think they use hundreds. They try to find as many supernova as possible. They have computers looking for them, and then they measure. They can take down the measurements, and then they find that there's a small acceleration, and it's an anomalous acceleration, or it was anomalous at the time. They expected the Hubble's law to be constant throughout the cosmos, but now it appears that the galaxies are increasing in speed as they move away from us, as the universe is expanding away from us. It's getting faster and faster. And so, obviously, this doesn't make sense. This is the collapse problem in reverse. So Einstein didn't like the original universe because it collapsed. And he thought that it should be stable. That's why he introduced lambda. And so now we have the opposite of collapse. It's accelerating expansion, which really doesn't make sense. You have to have energy to do this. It takes an enormous amount of energy to do this, and there is no energy budget for it. And so that's why it's called an anomaly. Dark energy is not a prediction. It is a failure of lambda CDM, or of expanding cosmology. Lambda CDM is the paradigm that includes dark energy and dark matter. But the entire lambda paradigm is what has failed. So how do we fix it? Well, dark energy is simple. A gravitational redshift model of Hubble's law is nonlinear. This means that there's going to be more of a redshift near the horizon than there is at 1 megaparsec. And so it's going to appear as though it's an acceleration. Like I said earlier, it's 3.49 times 10 to the negative 10 meters per second squared, which is around 2 times the dark energy measurements. Now, dark energy measurements at low Z are around half of that. They're around 1. They're around the same as the Mond constant. And then the closer to the horizon you get, the closer to this 3.49 you get. And I'm pretty sure that at the horizon, it's going to be exactly that 3.49. That's because of the way that they're interpreting it. And there's an enormous amount of interest around dark energy. And there's actually some funding and some projects that will attempt to try to pin down these Hubble values and the acceleration values. And so in the future, I think this is where I'll be focusing a lot of my energy, because I think that this is a good method to determine the difference between an expanding and a static paradigm. Now, I would like to argue that the expanding paradigm is not possible. I mean, it is possible if you have some energy, but there is nothing. There is no energy to do this. And so there's no reason to think that it's happening. The universe is just static. Let's go on to chapter 8.